harder. Woo. Section 1.9, inverses. Really quickly. I know on the board you can see that this notation is not the reciprocal. You wrote it, I emphasized it, but really quickly. Why would you think this was a reciprocal? The negative 1 exponent usually means flip a root, 1 over, right? If it's on bottom with a negative, put it on top. If it's on top with a negative, put it on bottom. This is the proper notation for a reciprocal, and you'll basically never see it in function notation. So if this does not mean to the negative 1 power, and you're never supposed to say to the negative 1 power, or think it, how do we read this statement once again? F inverse of x. Okay, notation, notation, notation. Multiplication? Oh, come on, you should know this. Multiplication? Be firm, be confident, be loud. Multiplication.
No. Yes.
That was a question. That was not confident. No, because it's F inverse of x, not times x, right? Real quick, before we go on, since we're maybe not looking at 1.8, how did compositions go in your homework for section 1.8? F of g of x. How'd we do? We did it all right? Composing and decomposing?
Decomposing was alright.
Don't worry, we'll look at homework when we can. We got here on Friday with the definition of an inverse. The point is when you put one function into the other, you know this, right? F of g of x. G of f of x, right? From section 1.8. When we put one inside the other, all the operations go away and only x remains. Same thing if we plug in the other direction, the exact same thing should happen. All the operations go away and we're left with x. What do I mean by operations? What are some things that mess up an equation and make it not just contain x? Give me some.
Limitation?
Yeah, but be more specific. What are some things in equations other than x?
Addition.
Addition, what else? Subtraction, what else? Multiplication and division, what else?
Roots.
Exponents,
Imaginary
radicals,
numbers.
roots, what?
Never mind.
Imaginary numbers,
Tables.
that'd be in like the domain problem
Yeah,
and
tables.
limitations. Could be logarithms, could be trig, we haven't seen them yet. Could be weird exponents, like fractional exponents, which means roots, or negative exponents. So what we're saying is find a composition and all of that goes away. All the addition, all the subtraction, all the multiplication, all the division, all the coefficients, all the extra numbers, only thing remaining is x, yeah? Okay, so then when we get over here, right, you didn't get this on Friday. And we have example number 1, finding an inverse function informally. Informally, what does that mean? It's just letting you know our whole switch x and y solve for y thing. That's informal, that's a shortcut. That is not technically the purely mathematical way of doing it, but that's okay. It's not a bad thing. But if we need to find the inverse of, and this is a very simple function because there's only one extra operation going on. Oh, it all disappeared. You're welcome. Now it's back. What's the one thing that we have to get rid of in order to get it down to just x?
4.
The 4. Now technically, some of you might get to the point where you are able to actually flat out answer on simple ones. I did not show my negative very clearly. Some of you might be able to see this and be like, oh, yeah, if you plug in 4x and 1/4 x, the 4's are going to cancel, you'll just have x. So some of you might be able to make that jump. But just to be clear in how we get there, f of x technically stands for what? What kind of values?
Y.
In general, y values. So if we want to switch the x and y, wouldn't we have something like this? Yeah? And then when we solve for y, what will we do with the 4? Divide it over. So inverse operation, you guys have heard that ever since you were in like math 6 or pre-algebra. Inverse operation, if it's multiplying, you divide. So you get y equals 1/4 x, but is that what I wrote as my answer? No. Remember, switch x and y, solve for y, and what extra little note did I add in on Friday right underneath that? Switch x and y, solve for y, and write y as f inverse, right? Is it still there? Make y equal to f inverse of x, okay? So when we switch to x and y and solve for y truly is 4x. So we cannot say that y is two different things. That doesn't make sense. We could call it like g of x, but we're going to call it f inverse of x. Now how do we verify? How do we prove that this is truly an inverse? Well, what does it take for an inverse to be true?
The inverse of the parent function.
The inverse of the parent function is what we kind of already did.
Oh, just plug it in.
But to make sure that we did it right, which this is an easy one, but to make sure that we did it right, we plug it in. We plug what in? We plug the inverse in where?
To the function.
To the function. So we plug in 4 times 1/4 x. I forgot my x. And what happens? What do I end up with? Good. It's an inverse, at least seemingly so. And how can we be extra super careful? Go the other way also. It should work both ways. So if I was to go into the inverse, it would plug in there, and I'd end up with 1/4 times plug in f of x. Does it work? Yeah, verified. No matter how you do a composition, no matter which direction you go, you end up with your final answer of x. Now, how many of you guys, if you had just walked in today, nothing was on the board, and I would say, what's the inverse operation of 4 times a number? How many of you would have gotten divide by 4? Maybe just a few. How many of you now seeing it, the inverse operation of 4 times a number, you're like, oh, it's 1/4 times. Do you see how the 1/4 and the 4th cancels? Okay. That's just the idea of an inverse, but does it get more complicated? Yes. But why?
Bigger stuff.
How messed up was that function? In the sense of how many different operations were going on? 1. Can it get worse than that? Sadly, yes. But before we get to worse ones, let's go ahead and just remove ourselves from the algebra for just a second. Let's talk about the graphical way of looking at it. Let's talk about inverses graphically. Functions can get more complicated, and if you look at this one up here, this one is more complicated. From the illustration, can you guys figure out how to fill in the line? Inverse functions are reflections across. In the illustration, you have f of x as the gray one, f inverse of x as the black one, and they do have symmetry, but not x-axis, not y-axis, not origin. They are symmetric about, or they reflect across, I should say. What line? This is the axis of symmetry, we could say that. Kind of, I mean technically they're two different graphs, so symmetry probably isn't the best way of saying it. But they are reflections across who? Y equals x. So if, like in that, you guys remember the 1.7, the transformation section in the back of our spirals, we did like 8 different transformations to one set of 4 points. That was number 9. You guys had one in homework also you had to do. If a problem was just to give you a graph and say graph the inverse, it didn't give you an equation, you couldn't put it in your graphing calculator, how would you do it? Think kind of like the symmetry. What's on one side of the y equals x line will be on the other. What's on one side will be on the other. Okay? So if you did have to take a graph, you weren't given an equation, how do you graphically deal with inverses? They are literally just reflections across. Okay? Now as you guys are looking at this, just because, even though we don't know exactly what this graph is, can you guys think back to your parent functions? Look at just the gray one. think back to your parent functions, what does he kind of look like? Which one? A cubic function, yeah. Now technically he could be a fifth degree function or a 7th degree function or a 9th degree function. If you're like, how is that possible? Graph x to the 5th, x to the 7th, x to the 9th on your own time. And compare it to x to the 3rd and be like, they're really similar, because they are. Sometimes. However, looking at this, it does look like a cubic. And what transformation kind of seems to be happening to him? Where are cubics usually centered? So it would have had a shift, seemingly, if I had to guess, a shift to the right and a shift. So we could make up something if you're really lost. And you could say something like, how would I shift it right?
-5.
Yeah, we could do like minus, and we could make this maybe like 5. -5 cubed, and then how do we shift it up?
Plus,
7 maybe?
Yeah.
Doesn't quite look like 5. A little bit more. Plus 7. We could make up a function, and it probably would look kind of close to that. But that's not the point if they're just having us graph reflections. That's not the point. However, let's go ahead and, just for sake of argument, because we were trying to practice a harder example, let's go ahead and find the inverse of what we just talked about. It's not necessarily the exact same function, but let's go ahead and use it and see if we could find that inverse algebraically if we needed to. So we had x minus 5 to shift it right 5. Oh, nope, it was a cubic function. Plus 7 to shift it up 7. Go ahead and practice again. Go find me the inverse of this function. We're pretending this is what that function was. It's not necessarily. And there were no tick marks labeled, so we kind of made up some. But find me the inverse. Ready, set, go. And the very first thing you should be trying to do is, what's your action step with inverses?
Switch the x and
Switch the x and y and solve for y. So who is y? Switch them with x. And break down each of those operations going on.
this is long.
Yeah, there's a lot going on. But how come? There's the plus 7, there's the minus 5, and there's a cube. There's 3 different things we have to undo. Right? How'd you guys undo? I just subtracted the 7 to undo the addition of 7 on the one side. How do I undo the cubed? What do you guys think of? Cube root. And technically, if you guys want to see what I'm doing. Oh, it wasn't plus 7, it was minus 7.
I did the worst thing possible.
Oh no,
I
what'd you do?
foiled
okay.
Ah! What'd you
the
do that
cube.
for?
The cubed.
That doesn't help, huh?
No.
So we undid the plus 7 first. Then we undid the cubed power because a cubed root cancels out a cubed power. We're undoing one by one. Basically reverse PEMDAS, undo the addition on the outside first, then undo the power second, and then undo the parentheses last. It's literally reverse PEMDAS. Then, I guess it's not time for that quite yet, but now it is. We had one final thing to do, and hopefully that one's not too bad, right? Now question. Where does that addition of 5, go.
Use parentheses.
You could use parentheses, but how do we do outside? Can't we just put it in front? With radicals, it's usually best to put it in front just for clarification, because if you put it on the other side, it's like, when does the square root stop? Did you write it properly? And then we end up with f inverse of x equals. Can you guys graph both of these functions? Just use your graphing calculator. Let's see if it kind of looks like what we had on the other page. Graphically, does it seem to match up? And if you want to, you can also graph y equals x as a third equation. So first you're going to graph your f of x, then you're going to graph your f inverse of x, then you're going to graph, if you want, y equals x. Do they truly look like reflections across that line? If you guys want to be super snazzy, those of you with like the colored screens, you can make them different colors. Those of you with the different styles, you can make like one bold and one dotted. Either way.
Good question.
It's in math.
Math.
If you can't figure out the cube root, is for most of you under the math, the x through, I don't think you put a cube in. Couldn't we also put it to the 1/3 power?
Okay.
Maybe that makes sense with inverses. A cubed is undone by a 1/3 power.
Just do this.
That's why we use roots.
Square. Zoom square.
We did +7, right? Is that what it was?
That's better. Zoom square.
How close does it match up with what we had in the page before?
Pretty good.
Not too shabby.
Zoom square looks.
Looks a lot better. All right, let's try it. Then zoom square, zoom number 5. Nice. So not only did we use our knowledge of parent functions to kind of figure out a good one for the original, but then we solved for the inverse, and yeah, I think we did a pretty good job. Look at what you guys can do. You can take a graph and figure out what on earth was there to begin with. At least for somewhat straightforward functions. Let's keep going. Oh, that's lame. That's just the answer. So if you guys had something in homework, don't even write this one down. But if it says sketch the graphs, we should always see this symmetry. Now guys, we're just looking at 2 graphs now. What did we do just now to be able to see it a bit more clearly? We didn't just graph 2 things. What else did we graph?
The lines.
Yeah, we graphed the y equals x line. That's one way. And we also saw, Luke, that was you, right? What zoom did you use?
Square.
Yeah. And that helps you see a bit more clearly with, what does zoom square do? Can you guys remember from the graphing calculator handbook?
Makes each unit even.
Makes each tick mark the exact same distance. That way it's not skewed or squished in a certain, distorted in a certain way. All right, let's keep going. Numerically, ruh-roh. Algebraically, switch x and y, solve for y, but make it y inverse, or I should say f inverse of x. Graphically, reflected across the y equals x line. Numerically, tables. Switch the x's and the y's. We talked about already on Friday about how the domains and ranges switch. But some of you might not have made the connection yourselves that if the domains and ranges switch, then the ordered pairs, yeah, they're going to switch also. And I'm not going to make you guys go to your graphing calculator and put in 2 different functions and go to the table and figure this out yourself, but hopefully just by quickly glancing at the information before you. 2 different functions we saw on the page before, graphically they're inverses, or they seem to be. algebraically, if we switch x and y and solve for y, this one would be the inverse that results. If we were to verify by plugging 1 in, it would undo the subtraction of 3 and the multiplication by 2, and vice versa works as well. They are inverses, and what do we notice about their points? What was the x and was the y is now the x is now the y, right? Or I should say, what was the x and was the y is now the y, and now the x. So every single point is going to be switched, which is why we have this location switch, this reflection across the y equals x, because literally the y's and x's flipped.
So we like table problems because they're easy, you just flip the numbers. Yep.
Should, as long as you make the connection. Some people wouldn't have made it on their own, and they'd be like, I don't know what to do. But if the domains and ranges switch, if all the x's of one become the y's of the other, then just switch, switch, switch as you go from the points of one function to the points of his inverse. Yeah?
The last point didn't switch. I wonder why.
How come?
Just kidding.
Math humor. All right. It's a good day. 1 to 1. All right. Now we have some terminology. We have some vocab. Lo siento, but here we go. We got this. We have some vocab. 1 to 1. What does it mean to be 1 to 1? You guys have heard this before. Actually, someone said it in chapel the other day, and I kind of laughed to myself. Who said it? 1 to 1. Oh, no. My pastor said it. He hasn't gotten to speak in chapel yet, but he will soon. 1 to 1. A 1-to-1 relationship. One of these refers to one of those. Strictly 1-to-1, not 1-to-2, not 2-to-1. Strictly 1-to-1, meaning kind of like with our example that we had a second ago. If we were to, I'm going to show you an example. If we were to take the function, let me make it black just for the parent function. Take an original function, let's use a different parent function, let's use, what's this one look like? Who am I referring to?
Square root.
Good. Alright. If we were to take the square root of x, now, you could think about it algebraically, you could think about it graphically. What would his inverse, let's just go graphically first. What would his inverse look like? Some of you are like, I'm not exactly sure, unless we graph
Go with
the y equals x line also. Let me show you the y equals x line real quick. It actually kind of goes through like that. So how is my inverse going to look? What's on one side? It's going to be on the other. Right? So what's there is now over there. And then, similarly here. Okay, there's the inverse function, right? Now we didn't do it algebraically yet, but just graphically. What's on one side is on the other in the sense of reflecting across the y equals x line. True? What 1-to-1 means is 1 point at one x value on one graph, the graph of the function, will map to, it's a very mathematical way of saying it, will map to 1 point at one y value on the inverse. Let me say it again. 1 point at one x value on the function will map to 1 point at, I misspoke, hold on. Where's our y? Make it a little bit clearer. Let's choose this one. There we go. I'll choose that one instead. 1 point at one x value on the original function will map to 1 point at one x value on the inverse function. The way I'd drawn it before, it kind of looked like the exact same thing, so it didn't really help. So 1 point on one function maps to, which means corresponds to exactly 1 point at one x value for another function. Why is that so special? Well, hold on. Let's go ahead and think about this. When would this not be true? When would this not be true? Well, let's go ahead and solve for the inverse algebraically real quick. So what would be the inverse of the square root of x? Can anybody just tell just by quickly being like, what would undo a square root? Squared. But why didn't I start with x squared? Why did I start with square root of x? What would happen if I started with x squared?
You would have the x-axis to the left of the x.
Yeah.
You would have stuff to the left of the y-axis.
To the left and right of the y-axis, right? If I had started with f of x is equal to x squared, and I told you guys to reflect this across the y equals x line, what would you have reflected?
It won't be a function.
Could you reflect it? Yeah. But when you reflected, you would have reflected this part, but what else would you have reflected? You would have also reflected this part. Uh-oh. Now, did we reflect it? Well, yeah, it's perfect. But is this the square root of x? Kind of. It's the plus or minus square root of x. There are two functions involving the inverse of the original. X squared is not invertible. How come?
It won't have some vertical lines.
Yeah, if I pick 1 point on this function at one x value, and I map it over here to the other, it is not unique. It is not unique for that particular x value. Or another way of saying it, its inverse fails the vertical line test. Now, how are we going to know if an inverse fails a vertical line test? If the original fails a horizontal line test. So, square root of x was what we would call one-to-one, shortcut of actually writing it out. Or we would say was invertible. Why? Because the inverse passed the vertical line test. When we inverted it, the inverse was a function, which is what we're saying. The inverse was still a function. But how could we have been able to tell that really quickly? Because the original passed the horizontal line test. So the struggle is vertical line tests you guys have done for a while now. A function is, well, an equation is a function. A graph is a function as long as it passes the vertical line test. So what's the horizontal for? Not to know whether or not something is a function to begin with, but to know whether its inverse will also be a function. So now we have an HLT as well. And what does it go along with? What does it prove? What does it show? Whether or not a function is invertible, whether or not his inverse will be a function as well. So when I come down here, can I say that this function is one-to-one? No. Why? His inverse fails as a function, which means the original fails as the horizontal line test, which means the function is not one-to-one or not invertible. Luca, go ahead.
So none of the even
Are going to
powers
be
are gonna
invertible.
work. Okay.
But that doesn't mean that we can't still discuss their inverse as two different pieces, right? But we just can't discuss it as one function. Does that make sense?
Mm-hmm.
So it's kind of like, in a sense, they have all the even functions will have an inverse relation comprised of multiple functions. Kind of?
Yeah.
Okay. So, don't even worry about writing this down. If I were you, I'd just pencil this down, because we're kind of running out of time, and that's okay, we can finish. But just look at this quick. What's invertible? Whose inverse will also be a function?
That graph.
Yeah, this one for sure. had to be quick, remember? We can just say 1 to 1. Check. Okay? Who's not invertible? Do we see it? That one's not, that one is. So the table. Now, some of you are like, I know who the table is. So, no, right? Because when you flip them, it won't be a function. So we can say it's not 1 to 1. But how can we also tell? Some of you thought once upon a time if there were repeated y's, it was not a function. You were wrong. This is a function. Each x is matched with one and only one y. However, if I were to switch these points, would it work for the inverse? Because you would have more than one for the inverse x mapped to more than one y, because for the original you have more than one y mapped to one x. Anyway.
I didn't see that.
Huh?
I didn't see that coming.
Oh, you didn't see that coming. Let me see where we are. I think we're just like homework helps. All right, let's try to do as many homework helps as we can. We have like 2 minutes. So if you want to do them with me, totally fine. If you just want us to get through them and then you check online or check on the video when you get to these types of problems, totally fine as well. I think number 1, we can kind of see is going to be a problem anyway, right? It's a squared. So let's check out number 2. How can we check whether or not this function is 1 to 1? We could graph it, or we could just find the inverse. And then see whether or not we can find the inverse and have it be just one answer instead of like a plus or minus. How do we find the inverse for number 2? Switch the x and y. Why am I trying to end on this problem? We still have a minute. It's actually like an SAT math question, kind of. To have a variable in more than one place and say solve for it. But how? Cross off stuff, because of course that's legal. You just kill kittens. That's horrible. So what else? Multiply. If you can't do anything, just change it up. And the only way to change it up is, well, undo the dividing by... Can I do this? What did I just do? I got him out of there.
Makes sense.
And I distributed, right? But how did that help? I still have 2 y's, but wait. What happens if I move him? Give me a second. And then subtract him. Wait.
You're still messed because you still have both.
Still so messed up, it's impossible. There's absolutely no way to get the y by itself.
Oh, whoa.
Or is there? Factor. And then you get f inverse of x to be. It's there for when you get stuck in
You
homework.
just ruined the homework.
I made it fun. Bye. Your Google Drive isn't working. Email me.